Guys, so welcome back. So as I was saying, Ms. Way, is that when you're doing a stretch along the x-axis, this unit matrix, normally you'd have 1, 1 down here. But because this matrix going to stretch along the x-axis, that means that you have to put the k value, replace this one above with the k value to stretch it along the x-axis. The same unit matrix, if you're going to stretch it along the y-axis, you replace the one here with a k value in order to stretch it along the y-axis. All right, and so if you're not sure what this stretch looks like, you can check back with the notes, because the notes is already posted. Check back with the notes and look at the shear. The shear is the same thing as this, the stretch guy. Look at them. All right. All right. So let us continue from here. Oh, sorry. I may have confused the shear. The shear is actually when you replace the zeros. The zero is the same unit matrix, but instead of putting the k along the ones, you put it along the 0. So the stretch is really, the stretch will look like a shear, but it will be different from the shear. The shear is what you would actually run parallel to the x-axis. What I'm going to ask you guys to do, just to be clear, just check the notes and look at the diagrams for the shear. And I don't remember if we have a diagram for a stretch, but just look at the diagram just to ensure that you understand what the shape should look like, guys. All right, so a shear along the x-axis, the k would replace the 0 above in the unit matrix. The shear along the y-axis, the k would replace the 0 below for the y-axis. All right. So all you have to do is just spend the time and become familiar with these matrices and know them different. All right, so that would be the end of transformation matrix. So what I'm going to do here, I'm going to stop share this, and then now we're going to move on to another topic. And the next topic that we'll be going on to is matrices. Sorry, not matrices, vectors. All right, guys. Now, vector, we're just going to start it today, and we're going to continue tomorrow. This will be our last topic for this CSEC program. There are other topics that we were unable to touch because of the time constraint. But for the practice workout videos, you will see examples of how to do questions that might involve other topics that we were unable to touch. So please watch those videos, guys, that were posted there to assist you in terms of working out some of these questions. All right, so vectors. Anybody have any knowledge of vector and know what we are referring to when we are talking about a vector? Anybody? Raise your hand if you know something about vector. All right, let's start. Anybody else? All right, Ms. Dorothy, can you start us off by telling us what you know about vectors? Ms. Darty, are you there? Can you respond for me, please?
Oh, sir, sorry. Sir, a vector is a quantity which entails the magnitude and the directions. Like when you talk about forces, like speed.
Okay. All right. Now, so you talk about magnitude and direction, but just saying magnitude and direction without being able to figure out what it really means in the real world sense can be a little bit, you know, hard to apply it if you don't understand what it means in a real world sense. Is there anybody else who understand anything about vector from a real world point of view? Anybody else? Miss Waysam, you know anything about vectors?
Sir, the only thing me remember, me know say with line, some line business, sir, but me remember no more.
Okay. Ms. Cabell, they teach you anything at school about vectors?
Just like some vectors, and I don't remember the other one.
What kind of vector they teach you about?
Like column vector. The top one is for the x-axis and the bottom one is for the y-axis. That's all I remember.
Okay, so you're really looking at what they refer to as vectors in relation to coordinate system, meaning when you're looking at vectors on a graph. So that's what you're learning about. But in the real world sense, there are certain natural things in the real world obey laws of vectors. And what Dorothy had mentioned about vectors earlier, she said that vectors have magnitude and direction. So that is the chief law of vectors. Now, what do I mean by that? If you think about any other quantity that you can measure, there are quantities in the real world that we can measure. We can measure length, right? Length is a quantity, so we can measure length. We can measure mass, mass, how much kilogram is in something, we can measure that. We can measure time in terms of seconds and minutes and so on. We can measure temperature.
Distance.
Yeah, we can measure distance. But the question is now, how many of those different quantities depend on a direction? How many of them, when you measure time, do we talk about the direction of time?
No, sir.
Right. When we talk about temperature, do we talk about direction of temperature? Do we talk about direction of temperature, guys? All right. Now, if we are talking about force, do we talk about the direction of force?
Yes, sir.
We're talking about speed. Do we talk about direction of speed?
Okay. Yes, sir.
We talk about velocity. Do we talk about direction? All right, so all this is saying, guys, is that there are some quantities when you're measuring them, you have to take a note of a direction. Those quantities that depend on direction, when you're measuring their size, the size is what we call their magnitude, how big the force is the size of the force. But we're not just we cannot just talk about a force by just talking about the size of the force. We also have to take into account which direction is the force moving in. We refer to, sometimes we talk about the force of gravity. Which direction is the pull of gravity going? Is it going up or is it coming down? Which direction force of gravity is taking place, guys? Up or down?
Down, sir.
Right. So gravity would be a vector quantity because it has a force which can be measured based on the unit of force, which is the newtons. But we can't just say the force of gravity is just 10. But we want to say that either the force of gravity is 10 newtons, and now you have to specify a direction, right? So it is 10 newtons acting towards the earth, or 10 newtons acting away from the earth. We know that that's not true, right? So vector quantities are those quantities that when you're measuring them, you have to take into account that their direction. Now, you have many different quantities in the world. Not all of them obey or has any form of rule when it comes down to direction. But those quantities that don't need for you to specify a direction, we call those quantities scalar quantities. So if you're just measuring the temperature, we don't really think about what direction the temperature is going. We just talk about how hot the thing is or how cool it is. And we use something like a thermometer to measure it, right? In that case, we are just measuring the size of the temperature, but we are not thinking about the direction of the temperature. So for temperature, that would be a scalar quantity. Could you think of any other scalar quantity apart from temperature? Go ahead, Mr.
Like the length and time, sir.
Well, length can be a vector quantity, right? But the thing is that if we are referring to length as a vector quantity, we don't call it length, right? So if we use the word length, we are referring to a scalar quantity. But if we are looking at length as a vector quantity, we call it by a different name. We call it displacement. So displacement is length in a certain direction. And that's a vector quantity. But when we're talking about distance, that is just length that is not in a straight line. And vector quantities are generally going in a straight line. Vector quantities don't take curve, right? So if you're talking about distance on a winding road, you would have to go around corner, measure the distance around the corner with those little curves and so on. That would not be a vector quantity. But if you're talking about an airplane going from Mobile to Kingston in a straight line, then that would be a vector quantity, right? And that distance would not be referred to as distance, but it would now be called displacement. Is that clear, guys? Raise your hand if you're following me so far. Guys? Okay, thanks much. All right, so our definition of vectors then. So a vector is a quantity which has magnitude and direction. So magnitude is simply the size of the measurement. And the direction is just simply which direction in terms of east, west, north, and south are bearings. So what direction it is going in a straight line, right? Now, for vector quantities, such as force, can anybody see the force of gravity? Raise your hand. Can you see the force of gravity? Ms. Wilson?
Sir?
Can you see the force of gravity?
No, sir.
Ms. Caveira, can you see the force of gravity?
No, sir.
Can you see the force between atoms?
No.
Right. So what I'm saying, most vector quantities, you really cannot see them physically. But we know that they exist. Because we know that if you have an object and you hold it above ground and let it go, sorry. In a second, my throat becomes a little irritated. Sorry about that, guys. But as I was saying, is that most vector quantities, we cannot really see the quantity itself like force acting. We can't see the force. The object can somewhat demonstrate that the force is acting in a straight line. For instance, when you hold a stone and you allow it to fall, that stone will fall in a straight line. So based on the object itself, we know that the object is experiencing some force on it, a pull on it in a straight line. But we cannot actually see the force. But we know that the stone is experiencing the force. Now, because of that, most vector quantities, we are unable to see the quantity being acting in the straight line. So because we cannot see it, we use a line segment to represent a vector quantity. So the line that we have here is not a vector, it's a line segment. But we use it to do what? Represent. So the line itself is not a vector, but we use it to represent a vector. Raise your hand if that is clear, guys. Ms. Cabrera, you understand what I'm saying?
Yes, sir.
Ms. Wilson?
Not quite, sir.
Suppose you watch a stone falling from above ground, Ms. Wilson. Is it What causing the stone to fall?
Gravity, sir.
So what is gravity?
The force that pulls things down.
Pulls down, right? Suppose there wasn't any gravity, would the stone fall to the ground?
No, sir.
No. Can you see the force of gravity?
No, sir.
Right, and that's what we're saying. We cannot see these vector forces or vector quantities, but we know that they act in a straight line. And because they act in a straight line, we use a line to say this is a vector acting through that line. So the line we have is just a representation of what the vector is. Now, you have different types of vectors, right? Vector, the term vector is just a term for those quantities that act in a straight line. It's not only force that act in a straight line. Force is just one vector quantity. You have velocity, which is a different vector quantity. You have acceleration, which is a different vector quantity. Displacement, different vector quantity. All of these act in a straight line and they're all vectors, but there are different types of vectors. But we're saying in order to be able to measure these quantities, we need something physical to represent them. So we use the length of the line to represent the vectors. And we use the actual measurement of a line segment, to tell you the size of a vector. So just like when we are doing graph and we're doing scale, and you say let x equal to 2 centimeters on the y-axis, or no, x equal to let x equal to no, that's not what I want to say. Let 1 centimeter equal 1 unit on the x-axis, right? It's the same thing that we're doing in terms of a vector. We're saying, let this length of line be equal to 1 Newton of force. So if we are dealing with the vector quantity such as a force, and we want to measure the size of the force, we have to have a scale length for 1 Newton. You're following what I'm saying? Ms. Waysom?
Yes, sir.
Right, so if you measure this piece and say this is 1 centimeter, so every centimeter you have a force of 1 Newton. Then the longer this gets, you find out how many centimeters can come out of it to tell you the actual size of the force. Is that clear to everybody? Ms. Darcy, is that clear? Ms. Waysom, well, Ms. Waysom mentioned that she's clear. Ms. Cavera, is that clear?
Yes, sir.
Miss Green, is that clear?
Yes, sir.
All right. So whereas the size of the line tell you the size of the vector, because we have a scale for that line. So every centimeter is 5 Newtons. So if we have 2 centimeters, we know that that is 2 Newtons, and 3 centimeters would be 3 Newtons, and so on. Now, the other important thing then is the direction. How do we tell which direction the vector is going in? So on the line, we put an arrow direction on the line to indicate the direction of the vector. Is that clear? So all we are saying, so all we are doing, we are using a line to represent a line segment. We are using a line segment to represent a vector with an arrow on it to show what direction it is going. The longer the line is, the bigger the size of that vector quantity. So if we're dealing with force and we have a scale for in terms of centimeter for a force, the longer the line, then is the bigger the force. the line itself is not the actual force, but the line represents the force. And the size of the line represents the size of the force. Raise your hand, guys, if you understand that. Okay. All right, so with that said, that is that is how we represent vectors. Now, if a quantity which is not a vector quantity, that quantity would be a scalar quantity. So what is a scalar quantity then? A quantity which has only magnitude, meaning only size, but you have no direction. All those quantities, we call them scalar quantities. So for length, that we're not considering any direction, would be a scalar quantity. Mass, that would be a scalar quantity. Temperature, time, all of these don't depend on any direction. So these are scalar quantities. So you should be able to tell what is a scalar quantity as opposed to a vector quantity. So force, displacement, velocity, bearings, all of those are vector quantities. All right, so with that said, let us move on. So as I said, we represent a vector quantity by drawing a straight line in the direction, in the same direction with a length directly proportional to its magnitude. Sorry about that, guys. The longer I talk is the more my coughs tend to act up. It's not as bad as yesterday, but because I'm talking a little longer, my throat gets a little dry. And there we go, it's acting up, all right? Just bear with me. So this is an example of a vector represented by a line and an arrow showing the direction. So the magnitude of the vector, meaning the size of the vector, we would actually measure the length of that line. And the direction of the vector, we would just look at the arrow that is showing us where the vector is going. Now, these are the various ways, that a line segment is used to represent a vector. So these are all different ways to represent vectors. So you can have a line segment with a common letter with an arrow on it. That is a vector. You could have a line segment with capital letters at the end point and the arrow showing which letter you start from and which letter you're ending up. So you start from A to B. So that is another way of representing vector. You can represent a vector on a graph by looking at the coordinates at the end point of the line. Now, if the vector is starting from 0 and the end point has coordinate 3, 4, you represent that in a column form, and that becomes a representation for that line. And that kind of representation, we call that position vectors when we use coordinates to represent them. All right, so these are how you may see different representation for vectors. Now, properties of vectors. Now, so these are the properties of vectors. Two vectors are equal if they have the same magnitude. And let's think of magnitude as the length. If they have the same length and direction. So two vectors are equal if they have the same length and direction. No matter where they are no matter where they are located in space. So if two lines have the same length and going in and pointing in the same direction, we say that they are equal. Two vectors with the same magnitude or same length, but different direction, they are not equal. So one of the important things for a vector to be equal, they must have the same length and they must have the same direction. So if you have the same length and the direction is different, the vectors are not equal. Now, property 3, two vectors are parallel if they have the same direction. Now, if two vectors are parallel, it doesn't mean that they are equal because they can have the same direction but different length. So when we say two vectors are parallel, we don't mean equal vectors. We just mean that the two vectors have the same direction. Is that clear, guys? Raise your hand. All right, guys. Now, the next thing that we know now is two vectors are antiparallel if they have opposite direction. So antiparallel vectors are going in opposite direction. It doesn't mean that they have the same length. It only means one going east and one going west. So the length can be totally different. All right. Now, in vectors, we also have a scale factor that we represent with K. Now, you would have seen in enlargement where we use K as a multiplier to enlarge your image or to enlarge a pre-image so that you get a larger image. It's the same thing that we do with vectors. The lines of a vector can be multiplied by some number K, which is a K factor. Now, the scale factor K has the same or similar effect as when you're doing enlargement. So that's why we use the same K when we are dealing with scale factor for vectors. The same scale factor that we use when we are dealing with enlargements, same scale factor we use for vectors. All right, guys. Raise your hand if you understand these properties that we have just gone through for vectors. Okay. All right. All right, good. So now these are some what we call equal vectors. Now, of course, two vectors are equal when they have the same length and direction. So if you look at this diagram down here, which of these vectors would be equal in terms of the examples?
Example
3, sir.
Example 3. And the reason would be they have the same length, they have the same direction. All right, guys. So we can say the vector A is equal to the vector B because they have the same length and same direction. Now, example 1. What example 1 would give you an example of? Would it be equal vectors?
They're both parallel.
These are parallel.
Parallel.
Right. So example 1 would be parallel vectors. But they are not equal in length, so they are not the same. They are not equal. Example 2 would give you what? What kind of example is that? They have the same length.
Non-parallel.
But they don't have the same direction. So these are not equal. And we wouldn't refer to these as antiparallel either. What would antiparallel mean? Antiparallel would be looking something similar like example 1, except that one arrow would be pointing in the opposite direction. Go ahead, Ms. Wesam. Ms. Wesam is saying something? Or you can lower your hand.
No, sir.
All right, so you get the idea of what equal vectors are. Now, parallel vectors. Two vectors are parallel if they have the same direction, but not necessarily the same size. So K is any number. The vector KAB is a vector that is parallel to the vector AB. So it means that these two vectors, one would be K times the length of the other. So one is actually longer than the other. So once you multiply by a K, and the K is a number greater than 1, it means that you're enlarging the length. If you multiply by a K value, which is less than 1, between 0 and 1, then this vector would be a reduction, meaning it becomes smaller, right? But parallel vectors don't need to be the same size to be parallel. Equal vectors are parallel, but you have vectors that are not equal in length, but they are in the same direction, so those are parallel. So in that case, one would be K times the other. And we say note, two vectors are antiparallel if they have opposite direction. So if the B was pointing in the opposite direction of the A, it would be an antiparallel vector. Okay.